Hey guys, here's our first example problem for chapter 5. It says that two forces are represented by the following unit vectors. Force 1 being equal to 2I minus 3J newtons, and force 2 being equal to 3.5I plus 2.5J newtons. And if these forces act simultaneously on a 5 kilogram object, we want to first determine the magnitude and direction of the object's acceleration, and then we want to determine the velocity of the object at 8 seconds if its initial velocity vector is equal to 2I plus 5J meters per second. So when we're looking to determine acceleration based on forces being exerted, we want to think about Newton's second law, which says that the acceleration of an object is equal to the net force exerted on it divided by the mass. And there's actually two ways we could go about solving for the magnitude and direction of the acceleration. The first we could do is find the components of the net force in the x and the net force in the y direction, and then find the magnitude and direction of the net force vector, and then use that to determine the magnitude and direction of the acceleration vector. But because we have to determine the velocity of the object at 8 seconds, I'm going to do it the second way that we could do it, which is to find the magnitude of the x and y components of the acceleration and then use those to find the magnitude and direction of the acceleration, because we'll need the components of the acceleration for part B. So what I'm going to do first is I'm going to find the net force in the x direction and the net force in the y direction, because if I find the net force in each direction, that can get me the acceleration in each direction. So the net force in the x direction, I'm going to add the x components of the two forces. So that'll be 2 plus 3.5 newtons, and that'll be equal to 5.5 newtons. And in the y direction, the components would be negative 3 plus 2.5 newtons. And that'll give us a y component of the net force equal to about negative 0.5 newtons. So now that I have the net force in each direction, I'm going to use that to find the magnitude of the acceleration in each direction. So the acceleration in the x direction is going to be equal to the net force in the x direction divided by the mass, which would be 5.5 newtons divided by 5 kilograms. And that would give me an acceleration in the x direction equal to about 1.1 meters per second squared. And in the y direction, I'd have an acceleration equal to the net force in the y direction divided by the mass. And so that would be negative 0.5 newtons divided by 5 kilograms. And so my acceleration in the y direction is going to be equal to negative 0.1 meters per second squared. So then once I have the components of the acceleration, I can just use the Pythagorean theorem to find the magnitude of the acceleration vector, which would be equal to the square root of 1.1 squared plus negative 0.5 squared. And I should have units there, but I'm being kind of lazy, so sorry. And so when I take the square root of those two added together when they're squared, I'll get a magnitude of the acceleration that's about 1.105 meters per second squared. And then I can use tangent inverse to find the direction. Take a second always when you're finding direction to sketch out your component vectors so you know which quadrant it's in. So I'm going to have 1.1 meters per second this way, negative 0.1 meters per second squared that way. So my acceleration vector, oh, that looks bad, is going to be in that direction, which looks like it would be in the fourth quadrant. So I'll do the tangent inverse of negative 0.5 over 1.1, opposite over adjacent, and I'll get that the angle is about negative 5.77 degrees. And to get that counterclockwise from the positive x-axis, we'll add that to 360. So 360 plus negative 5.77 degrees. And that's going to give us a direction of 354.23 degrees. So our acceleration is going to be equal to 1.105 meters per second squared at 354.23 degrees, like that. And then we'll put a box around it to make it easier to find. Okay, so next We're going to determine the velocity at 8 seconds if v initial is equal to 2I plus 5j meters per second. So this is actually going back to the last chapter, chapter 4, where we looked at two-dimensional motion. And so I'm going to think about my givens and unknowns here. So I know the time is equal to 8 seconds. I have the initial velocity vector. I have my components of the acceleration, and I'm looking for v final. So with these 4 givens and unknowns, this tells me I'm going to use the equation that v final equals v initial plus a times t. And I'm going to find the v final in both the x and y direction. So I'll do v final in the x direction will be equal to 2 meters per second. That's the initial velocity. Plus the magnitude of the acceleration in the x direction is 1.1 meters per second squared. We found that in the last problem, or the last part of the problem. And then times 8 seconds, so v initial plus a times t. And that'll give me a final velocity in the x direction of about 10.8 meters per second. And then in the y direction, I'll do v initial, which was 5 meters per second. Plus my acceleration in the y direction was negative 0.1 meters per second squared times 8 seconds. And I'll get the final velocity in the y direction is about 4.2 meters per second. And then same thing, I have my components of the velocity, so I can use the Pythagorean theorem to find the magnitude of the final velocity vector, which would be, equal to the square root of 10.8 squared plus 4.2 squared. Again, I should have units, but I'm being lazy. Do as I say, not as I do. And so the magnitude of my final velocity vector will be about 11.59 meters per second. And then the direction will be my opposite over adjacent, 4.2 over 10.8. And the direction of my final velocity will be about 23.61 degrees. And since both of these components are positive, I know that'll be in quadrant 1. So I can say that the final velocity is equal to 11.59 meters per second at 23.61 degrees.